Welcome back to AI Citizenship for Clinicians. In our last lecture, we introduced the field of natural language processing, the challenges the field has faced in getting computers to understand and work with human language, and a broad overview on how recent advances in scale and techniques have overcome these challenges in the creation of language models. In this lecture, we will discuss present day, how language models are built, and how they can be implemented. So why does a clinician who plans to just use these tools need to understand their construction? The motivation behind this lecture is the classic Feynman quote, "What I cannot create, I do not understand." Along with the lesser-known medical corollary, I am most dangerous to my patients when I'm using something I don't understand. LLMs have a number of ways they can be biased, inaccurate, or fail. Many of these are a direct result of the processes used to build them. In order to understand, identify, and guard against these failures, it is important to understand why they might be present. After providing this background knowledge on model construction, we will discuss pitfalls and bias in LLM in the subsequent lecture. As a reminder from last lecture, LLM are in essence AI models that have been trained on large amounts of text data to be extremely good at predicting the next word in a sequence, given a previous sequence of words. So how do we get a model that understands human language so well it can produce speech at or near human levels of accuracy? Going back to concepts introduced during lecture 1.1, there are a few broad categories for how we train a model to predict the correct output given an input. The first is supervised learning. In this, the model is trained on a set of gold standard input and output pairs, with the hope that it will learn the patterns in the input that correspond to the correct output, so that it can eventually predict the correct output on a new input sequence it has never seen or trained on before. The term supervision refers to the fact that the input-output pairs used during training must be labeled by an external entity, or supervisor, usually a human who knows the ground truth answer to each question or input posed. Self-supervised learning is a similar concept in that the model is provided a set of correct input-output pairs to train on. The self in self-supervised lies in how we create these pairs. Instead of requiring an external supervisor to determine the right output, part of the input is masked or hidden, and then the model is asked to recreate the hidden part. We will show a concrete example of this later in the lecture, but the advantage of this is that it's much more scalable in many cases, as it frees training from the requirement of a human needed to label each right answer. Finally, there are reinforcement learning techniques, where instead of providing correct labels, there are instead positive or negative rewards for outputs, depending on how well the outputs align with the desired outputs. It's hard to diagram the pipeline for development of an LLM that is accurate across all the major developers currently in the space. However, a fair representation of an ideal pipeline is as follows. First, you would accomplish pre-training, training a large model on as much quality text as possible to impart an understanding of language construction and a foundation of general knowledge. Then, you would provide training data specific to the task you want to accomplish, whether it's writing a clinical note or taking patients at ED triage or classifying a radiology report as cancer or not. Then, you would apply strategies to ensure that the output the model gives you conforms to the standards, formats, and restrictions you might want to place upon it. Finally, you would start to connect it to the data or additional systems or models that are required for the task, as well as ensure the input and output to the model are optimized as much as possible. Again, this is the ideal pipeline of model construction, but the typical implementation is slightly different. So in practice, the pipeline is slightly different. Rather than specializing the model for a task and then aligning the output toward the correct standards, formats, and ethics desired, typically we swap these procedures. That is because of cost. The energy and hardware cost for pre-training is currently in the billions of dollars. Subsequent to this, training a model to respond appropriately, along with additional safety constraints and attempts to avoid regurgitation of bias or harmful text, can often cost millions of dollars on top of this. Given this alignment cost, it is often easier to use the alignment step already completed within the company that developed the language model. One can then take this model and specialize it by providing training data specific to answering the question desired. though the power of current LLMs means that this step is not always required, and sometimes the LLM has strong enough accuracy for a given task out of the box. The caveat we need to mention here is that by doing the specialization after model alignment, there is a chance that the model unlearns some of the training done during the alignment step. We won't dive into this concern further in this lecture, but bring it up to explain why alignment would occur after specialization in an ideal model pipeline. Finally, there is productionization of the model and user input, both of which are critical for successful and safe implementation. At the end of this lecture, we will discuss the different categories of modifications that can be applied around LLMs. So let's walk through and discuss how we accomplish each of these steps. The first step is pre-training, which is exposure of the model to what a language is and how it's constructed. As mentioned, for the highest performing model, this costs billions of dollars and consumes huge amounts of energy and time to complete. Creating these pre-trained models, rather than just trying to train a model starting with the specific task you want to accomplish, has been shown to improve generalizability, learning efficiency, and overall performance. Pre-training is typically accomplished through self-supervised learning approaches. An example is demonstrated to the right. In self-supervised learning, part of the known phrase is hidden, and the model is asked to regenerate the missing portion. A key advantage of this is scale. You can automate this process of masking different parts of a document and asking it to regenerate it, and this can be done billions of times without requiring manual creation of a training dataset. The original goal of this process was to create a model that has an internal representation of language entities. However, because modern LLM have so many neurons, they can often learn not just language structure, but also the general knowledge present within the training data they are learning from. For example, facts about the world or specific styles of writing. It's important to understand what kind of text was used to train modern language models. Ideally, we would want to expose the model to all the different ways language can be utilized, from haikus to prose to computer coding languages. And in order for it to learn the construction of each of these, the model would ideally see thousands to millions of examples. As I mentioned in a previous lecture, the largest models like GPT-4 were trained on 5 to 6 trillion tokens, which would fill about 750 miles worth of books stacked one on top of one another. As you might imagine, companies run out of great works of prose and poetry to train on somewhere in the first couple miles. So what makes up the rest? Much of the rest comes from the internet. That can include digital books, news articles, peer-reviewed publications, etc. However, it can also include blogs, Reddit forums, and Facebook pages, with all the typos and misinformation that's inherent to each of these. While the scale of web-based data is necessary for the pre-training step, it does introduce many challenges. The extraction of this data is automated and can lead to poorly parsed or garbled language in some portions. Even after trying to remove these sections of garbled text, much of the discourse on the internet would not be ideal to replicate, either due to poor quality, inaccuracies, or objectionable material. There is also multiple inequity issues here, most glaring of which is that the majority of the internet uses the English language, which likely leads to models using this data for pre-training to be better with English than other languages. Finally, there is a growing concern that as AI takes over the internet discourse, either through as a tool used by humans or direct text generation, more and more of the training data will be written by AI itself. The second step is alignment, which is the set of processes to conform the output produced by the model to what is expected by the model creators. This frequently involves making sure it has the appropriate size, content, and format, and often includes ethic or moral alignments to avoid production of objectionable content as defined by the people constructing the model. Why do we need alignment? There are a few reasons. The first relates to poor quality of the pre-training data mentioned above. Because there is no human filter on what data is used for pre-training, much of the quote-unquote knowledge learned by language models during pre-training can either be incorrect or out of date. Just to help drive home how this might happen, a highly publicized flub from a recent language model suggested that President Obama was the first Muslim president when asked a question about Muslim presidents in the United States. This is likely because there were so many examples in the training data of misinformation written about President Obama and his religion. Alignment can help improve accuracy and knowledge within the language model. Safety or ethics is another motivation behind alignment steps. To provide another salient example of the importance of these considerations, a chatbot designed to help with eating disorders started offering dieting advice with anorexia nervosa. Often, alignment training is done to prevent models from providing dangerous answers or even having it avoid some topics entirely. Finally, a less exciting reason is to ensure the format of the output is ideal. For example, at this point, we expect the chatbot to provide some reasoning behind each answer unless we ask otherwise. However, with pre-training alone, this format is not guaranteed. Alignment can help provide examples to the model for the expected output structures and formats. A number of alignment strategies are available to accomplish these goals. These typically take the form of reinforcement learning described previously, where answers that better conform to the expectations of an observer are rewarded, with worse answers being negatively incentivized. One common way that directly interjects human perception into model answers is reinforcement learning with human feedback. In this approach, answers are shown to a human, and based on the rating, the language model will refine its strategy to align with the human judgment. It should be clear that this process may not just remove biases from the model incurred through the training data, but may also introduce biases based on the subjective perceptions of the humans doing the feedback. Using a cartoon example, if during the process an animal owner asks why their cat is acting selfish, the LLM may originally be predisposed to respond that the cat is selfish and mutual love is an incorrect projection. However, during alignment, this type of answer may be disincentivized, leading to an LLM post-alignment that is more conciliatory and kind, even if it may be less accurate. Again, these first two steps take place at large tech companies like OpenAI, Anthropic, or Meta. The results are the models they release, such as ChatGPT, Claude, or Llama 3. Much of the time, these language models may be powerful enough after just these two steps to complete tasks of interest to medical companies or individuals. However, for some complex tasks, further specialization and training may be needed to be applied to improve the performance prior to safe and effective use in a clinical setting. Specialization of language models often is accomplished through supervised learning approaches. As a review, these approaches provide the model with a set of question-answer pairs focused on the specific task that we want the model to excel at. These are typically constructed through manual labeling or some other approach. Whether the task is document classification, increased medical knowledge, or better text generation for medical documentation, supervised learning can be an effective way to take a model that isn't good enough out of the box and increase its performance. These first three steps constitute the creation of the model to be used. However, successful model utilization still requires ensuring it is optimally integrated into the system and user interactions to produce a safe and useful product. There are two components to this. The first is productionization, which constitutes all the pipes required to connect a language model to whatever other elements of the medical record or patient experience that it will be used to modify. The second is prompting, which is how to format the input sequence of words to best ensure the accuracy, safety, and reliability of output. We will discuss both, but wanted to plug our advanced topic lecture on practical prompt engineering we will be recording soon. Once you have an LLM, implementing it within an existing healthcare system can often be the hardest part of the process. This can be broken down into input optimization, output optimization, and LLM integration with external tools and resources. First, user or medical input has to be identified, and the way in which that input will be sent to the LLM has to be constructed. After this pipe is created, standardizing and optimizing this input is often required to ensure optimal performance of the model. For example, if a model is set up to answer verbal medical questions from a clinician that has been transcribed into text, a few steps have to be accomplished. First, cleaning this transcript to remove things like background noise or irrelevant speech. You also have to decide if you are going to allow patient health information to be included and find a way to remove it prior to sending it to the LLM if it shouldn't be. Regardless, an automated way to send this information securely to an LLM must also be constructed, and so on. Prompt engineering can also be applied within these pipelines, such that your constructed system automatically adds additional information that you have experimentally found improves model performance. Prompt engineering, either within engineered workflows or during end-user experience, should not be overlooked, as time and again it is proven small changes in input can have major ramifications on the accuracy of the response. Output control is similar to input control. Once a response is generated, external processing and the connections to the end destination must be created for efficient deployment of the LLM. Major concepts in output control within healthcare context are triaging and gatekeeping. Gatekeeping is the concept of putting limits on what the model is allowed to do. Within our field, a common gatekeeping mechanism is to block any output from an LLM that may be perceived as giving direct medical advice. Triaging is the idea of changing the next step or where output is directed to, based on the inputs created. For example, a question posed to a patient-facing chatbot may require a simple description of the side effects. But if an intervention is required, additional outputs or even direct actions such as EHR message or emergency call to provider could be initiated by the model. Finally, LLMs do not have to work in isolation and can often be most effective when they are allowed to work with other tools, computer systems, or databases. This improves the LLM's abilities in computation, allows it to make modifications in the EHR, or send communications to healthcare professionals. These are just a few examples, but people are constantly introducing ways to integrate LLM in new, extremely clever and powerful systems. One of the most commonly used methods currently is retrieval augmented generation. This process will come up a lot in discussions of current LLM implementations, so it's worth a brief overview. In this method, a language model is provided a specific text or database of text and asked to base answers on information within this database. By forcing the answers of the LLM to be based on a specific set of documents, such as an individual patient's medical record or a trusted textbook, you can better ensure accuracy. In a medical context, this can be especially important for accurate information retrieval from proprietary datasets like EHR records. Other uses include connecting an LLM with the internet and can allow it to stay up to date on information that may have occurred subsequent to the original training. You can even have it write its own code and execute it if run on computer programs within the local system. One thing worth discussing is the bifurcation between proprietary versus open LLMs. Proprietary LLMs are models in which the full model has not been released for download, and therefore does not allow complete control by the user. This includes the OpenAI GPT models and Claude from Anthropic. Even if these companies did allow full download of the model, many are too large to run without the infrastructure at a major tech company. These large proprietary models typically exhibit better performance out of the box, but with significant trade-offs. They typically cost money for each use and have more limitations in how they can be modified for specialized tasks. Because the company can change the model at any time, there are also issues around model stability and reproducibility. Finally, maintaining patient privacy with proprietary models can be more challenging and costly, as any input is sent to an external entity. So any use of these models with PHI typically requires specific contracts between the medical organization and the tech company. Open models, on the other hand, can be downloaded and run locally, whether that is on a personal computer or the IT system within the medical campus. These have much more flexibility in how they are used, including the full ability to specialize for specific tasks, easy implementation with PHI, and relatively cheap run cost. However, because they are smaller models, it can be challenging to achieve the performance seen in larger models, at least at this time. In summary, the process of creating and deploying an LLM for medical use has 3 or 4 distinct steps. 2 of these steps are accomplished by the major tech companies like OpenAI or Meta, while the last steps can be done by smaller companies, local health systems, or even you. While few of the clinicians watching this video will have to be intimately involved with most of these steps, understanding their purpose and how they are accomplished is critical to understanding the potential pitfalls and biases that can arise in LLM during their implementation and use. We will cover these in the next lecture.